5.4. Today we're going to look at some application problems as they pertain to logarithms, specifically in physical sciences like chemistry, biology, and physics. To get us started, we're going to talk a little bit about pH. The thing that determines the pH of a substance is the hydronium ions and their concentration in a substance. And the concentration of these ions in a substance can vary greatly from a number that's very, very small to a number that's very, very large. If we were to graph these numbers, very, very small numbers, very, very large numbers, it'd be hard to determine the shape of the function that we're looking at. So in order to make it easier to compare these quantities, we use logarithms. And the pH scale is an application of the logarithmic scale. The logarithmic scale is something that is used in situations where variables can range over many, many orders of magnitude. As an example, many, many powers of 10. If we're graphing a number like 10, and if we're graphing a number like 10 to the power of 5 on the same graph, the scale is going to be so far off as to make looking at it almost meaningless. So we're going to explore looking at that logarithmic scale today. We're going to start with the pH scale. So if you've taken chemistry, you know this is how we measure the acidity or alkalinity of a chemical. The equation for pH is pH is equal to the negative log, the negative common log of H+, where H+ is the concentration of hydronium ions. You can see this table in your textbook, but right now, if a pH of something is 1, that's very, very acidic, and pH ranges from 1 to 14, something that's very, very alkaline, and then a substance that's neutral has a pH of 7. We're talking about concentration in moles per liter. That would be a hydronium ion concentration of 10 to the power of -1 for something that's very, very acidic, up to, or I should say down to, a concentration of 10 to the power of -14, a very, very small number for something that's very alkaline. So let's look at an example of this. We said our equation is equal to the negative log of the hydronium ion concentration. And in tomato juice, there's a concentration of 0.0001. pH is equal to negative log of 0.0001. And this is something we can evaluate directly on our calculator. So pH is equal to negative, calculating the common logarithm of 0.0001. I get -4. So -1 times -4 is +4. And the pH of tomato juice is 4. Okay, similar question. Blood has a pH, similar question. Blood has a concentration of ions of 4 times 10 to the power of -7. So we'd like to know if blood is acidic or alkaline. So we can plug this into our calculator. The negative log of 4 times 10 to the power of -7. I get negative 6.3979. We'll round that to negative 6.4, which ends up being positive 6.4. If we look at our table, value of 6.4 is about here, which means that blood is a little bit acidic. orange juice has a pH of 3. We'd like to figure out the concentration of hydronium ions in orange juice. So I'm going to bring the negative over to the other side. Then I'm going to rearrange this like an exponential. So this is going to be 10 to the power of negative 3 equals the hydronium ions. Ten to the power of negative 3 is 0.001. So orange juice has a concentration of 0.001 moles per liter. So then the next question is asking us which has a greater concentration of ions, orange juice or tomato juice, and by how much? So looking back at what we did, we found that orange juice has a hydronium ion concentration of 0.01. Sorry, 0.001. Tomato juice has a concentration of 0.0001. So by how much more does orange juice have a concentration of hydronium ions? Well, we can take these two numbers and divide them. And when I do that, I get an answer of 10. So I can say that orange juice has 10 times the hydronium ions. So that's just one situation where we see the use of logarithms in the physical sciences. We're going to do 2 additional examples in class on Monday. I hope you all have a good weekend. Thanks for watching.